what I'm going to do is I'm going to integrate this function here, eiz over z, along this path, the path shown in red. And I note that this integral should be 0 because the pole of this is at 0 plus 0I, dividing by 0. And we're very deliberately avoiding that pole there. So integrating along this path is supposed to make 0 for this function here. We're deliberately avoiding the pole. So we can say that the integral for alpha plus for beta plus for gamma plus for delta should equal 0. That is, the alpha integral and the gamma integral should equal minus the beta integral minus the delta integral. Or for brevity, the alpha plus gamma integral here, eiz over z dz, that will equal minus the beta, eiz over z dz, minus the gamma, eiz over z dz. Now we'll have to talk about path parameterization. So for the beta one, we can say the path is in the form of z equals small r e I theta, or if you prefer, that's r e cos theta plus I sine theta. And you should note that the z would be r I e I theta, which is actually, sorry, I forgot my d theta, which is actually I times z d theta. And you can do likewise for the gamma path, but with the bigger radius or instead. So we get now the integral along alpha plus gamma. I just will now do a replacement here. So the beta is the small radius. So that'll be minus integral e I z, which is r e I theta over z, and then dz is I z d theta. Oh, I should mention, of course, that the theta goes from 0 to pi because it's a half circle. The z's cancel. And then the next one is basically the same, except it's replaced with the bigger r. Again, the z's cancel. D theta. Okay, so integral alpha plus gamma eiz over z dz equals. Now, what we're going to do now is we're going to take the big radius going to infinity, the small radius going to 0. That's what's going to happen now. So this arc here gets pushed out to infinity, these extend to infinity, and this starts to shrink down. So we'll apply that now here. So you can see what will happen to alpha and gamma. They will grow and fill in the basically the x-axis, minus infinity to infinity. Now, what will happen here? Because r is really small, and given the nature of this function and this limit, we're allowed to replace this with its linear Taylor series or Lorentz series expansion and take r going to 0. So we'll have minus the integral 1 plus I or e I theta d theta, like that. And that is also being multiplied by the I. And then this one here, multiplying by the I. Now, this one here, I think it's worth expanding. So that's EI or cos theta plus I sine theta. Now, if you multiply that out, the I multiplies the cos, that's fine. But when it multiplies the I here, it makes minus 1. So what you'll have is I or cos theta minus or sine theta d theta. And let's not forget we have to take the limits as well. I'll just write that limits here for short. So this integral minus infinity to infinity eiz over z dz, that will equal minus I integral beta 1 plus I or, well, yeah, let me just leave that for the moment. I don't want to do too much in one step. And this will be minus I integral, and I'll just separate this out, E minus or sine theta and EI or cos theta d theta. Now note here, if you calculate the absolute of this and the absolute of this be I cos theta, and then we'll bring the or outside. This is less than or equal to 1 with a power or, and this one here is just going to the shrink. That is, when you take or going to infinity, clearly that's going to go to 0, and that's going to go to 0 as well. So what will happen is this piece will vanish. So this outer integral gets pushed out to 0. So now it's all going to come down to what this integral is here. So the critical one now, minus infinity to infinity eiz over z dz, that will equal this path integral here, which will be minus I 0 to pi. And you know what, let's just go straight into integrating it. So that would be theta plus, and then integrating this, we'll have to divide by the I, so that would be or E I theta 0 to pi. Okay. And again, that or gets pushed out to 0, so you're just going to get here minus I pi. Okay, that's great. We're nearly finished. So now we have shown that the integral from minus infinity to infinity of eiz, which is going to be cos z plus I sine z over z dz, that's equal to minus I pi. Yeah. Actually, you know what? I made a mistake. I'm sorry. I just have to go back, explain. I put the limits in backwards. Didn't I? Yeah, because if we're, for example, if we start here and go around like this, the angle actually goes the other way, pi to 0. So that would be plus I pi. But that's my mistake. Okay, now I've corrected that. So we should be good to go. Okay. So now we have the integral of minus infinity to infinity cos z plus I sine z over z dz. That's equal to I pi. So that's minus infinity to infinity cos z over z plus I sine z over z dz. That's equal to I pi. But cos is an even function, z is an odd function. So in total, this is an odd function. And because the integration was symmetric, it means that this integrates to 0. So now you have minus infinity to infinity I sine z over z dz. But the z is really just a dummy variable, so I'll just change it to x since we're only on the real axis. So sine x over x dx, that's equal to I pi. The i's cancel, and we have our result. Minus infinity to infinity sine x over x dx is equal to pi. If you want, though, you can continue a little bit more. Because this is an odd function, and this is an odd function, so in total it's even. So that means we can say that the integral can be replaced by twice 0 to infinity sine x over x dx equals pi over 2. But this here is the SI function, 2 SI infinity. Oh, sorry, I did 2 steps in one, didn't I? So I should have just said pi. I was going to divide by 2 on the next step. So 2 SI infinity, that's equal to pi. So then we get SI infinity, that's equal to pi over 2. Okay, there we go.